Hey there, everyone. My name is Ryan Schubel. Welcome to my data science channel. In the project today, I want to take a look at primary market deal allocation, and we're going to analyze this using Python Jupyter Notebook. Okay, so I'm going to create some hypothetical data. It's going to be pretty realistic, but this is actually like all private and completely confidential data. Like you'll never have access to this unless you work in an investment bank putting together IPO deals or something along those lines, right? If you're one of the bankers or lawyers, but the allocation details are like who gets how many shares and at what price, and which trants they go to are considered proprietary, right? So I understand basically how this works. I had to do some research, but I'm going to have to make up the data because this real data is not in the public domain, right? You can get some things like SEC filings and price prospectuses and things like this, but they don't disclose the total number of shares offered, the final pricing, and things like this. So it's going to be a realistic example of how these things are done. But again, we'll have to make up the data because outside of the iBank, like you would never have access to this actual data. And why would we even do this type of analysis? Just to understand IPO modeling, how shares are allocated to different investors, how tranching works, prioritization in the subscribed deals that go out, right? Any kind of relationship management, that's more on a personal level. That's not really an analytical type of thing. But revenue optimization certainly is. Compliance and transparency are relevant. Investor tiering strategies, feedback loops, internal performance metrics, right? These are all tracked to see how things can be improved. Investor loyalty building and avoiding share flipping. Okay, so that's important too. This is where past participants' behaviors can be modeled to reduce allocations to short-term traders whose harm might be more good than the IPO's performance, right? You want to try to prevent that. And strategic deal participation. Okay, so let's just jump into it. Here is my synthetic, but I believe pretty realistic data. We're going to create a small data frame with different investor IDs. This could be a name, more likely it's an ID. Investment tiers, this is tier 1 through 3. Relationship scores, past deals participated in, requested number of shares, and then was they actually allocated or was it not allocated to this investor? Okay, so that's sort of the basis for the analysis, and we can actually use a simple machine learning method here. This is going to be a random forest classifier. So I have many videos on my channel here all about machine learning and data science, so you can take a look at how these machine learning models work if you want to get more into it. But basically, we have an X variable, which is independent, and a Y variable, which is dependent. I want to try to make a prediction based on historical data. We can see over here, here's the allocated. I'm dropping investor ID and allocated because I can't test the data on itself, right? When you're trying to make a prediction on something, you can't use the predictor as a variable because everything is going to, if you train the model on that variable, it's going to really mess up the model because it's thinking it's trying to make a prediction, but it's actually using that as an independent feature. You definitely don't want to do that. And you'll never use an ID because that has no bearing on whether or not something is being allocated or not. So hopefully that makes sense. I have several videos on my channel if you want to get more into all the independent variables. X is independent and Y is the dependent. So again, we have the historical data here. I'm trying to do testing and training on the model. It's doing the fitting down here, so everything worked fine and making predictions. Now, honestly, these predictions are not great. You want to see these numbers higher, 0.7, 0.8, 0.9. That would be great. These numbers are a little bit low, so the precision, recall, and F1 score are a little bit low, but I just want to illustrate the point of how we can use this to make a prediction. We can enhance the model many, many different ways to boost these performances, these performance metrics, to get higher precision. Again, you want to see at least 0.7, 0.8, 0.9 is better. The higher the better, recall, and F1 score. But in this case, I don't really care about these scores. I just want to go ahead and set up, train, and test the model and try to make some basic predictions. So I don't really care about these right now. I just want to show you that that isn't an option if you need that. Okay, so let's move on to the next cell here. We have features as X columns. I want to try to predict which features are the most important to predicting this Y target variable. Remember, we're looking at a bunch of features. We have this over here, investor tier, relationship scores, past deals, participated, and requested shares. We're dropping that because that's what we're trying to predict. And we're dropping the ID because the ID is completely irrelevant, has no bearing on the prediction, right? But I want to understand now which features now have the most statistical impact on the target variable. And this feature importance exercise will tell me that, okay, everything comes from here. It's like literally just one line of code. Once you have the model set up, here's the model right here. Okay, so the model comes from here. We're in the forest classifier. We fit the model here. We're making predictions here. That's the way you see this small matrix down here. The model is already set up, trained, and tested. We're extracting the feature importance metrics from this, right, and using this as importances and then plotting that, right? If I do Control F, we can see the importances right here. So the most important features I'm predicting whether or not a deal will be allocated, right? Whether a client will receive an allocation are based on relationship scores. That makes sense. If you have a better relationship with your client, you're probably going to give them more of the overall deal. You're going to do more transactions, right? Requested shares, if somebody wants more, you're probably going to pay them more, right? I think that's pretty intuitive. Past deals participated, again, totally makes sense. If you participate a lot, if you have a good relationship, and if you request a lot, you're probably going to get more shares. Whether or not the shares are considered tier 1, 2, or 3 has very little relevance to whether or not shares will be allocated to any specific individual, or not really individual, but enterprise or business unit or something like that, right? So this type of analysis helps syndicate desks prioritize investor-based behavior and loyalty, manage compliance with allocation fairness regulations, right? Again, you can't drop all the eggs into one basket. You have to kind of like distribute these in an efficient, but in a fair and decent way, right? If you want people to have repeat business with you. And that's the name of the game: repeatable, sustainable, predictable, right? And simulate what-if scenarios based on investor behavior or deal characteristics. And again, even though I made up the data, I think it's pretty realistic. If you have more features over here that you can use for the training and testing of the model is going to perform better and better. One reason that we're seeing kind of low scores over here, again, higher is better. We only have 1, 2, 3, 4 features to train the model on. That's not a whole lot, right? We'd like to have a whole bunch, at least a dozen, couple dozen, several dozen. The more data you feed into the model, the better decisions it can make, because it's going to learn all these intricate relationships, right? And these are non-linear relationships. That's why we're using the random forest classifier. But the more you put into the model, the better the performance, right? So I hope that makes sense. Here's the simulated data set showing IPO deal allocation histories across multiple deals and investors, right? The investor profile will show their tier, the relationship score, past participation rate, things like this. We're training the regression models to make predictions. This is actually a classification. That's a mistyping there. Fix that up. Analyze which factors have the most statistically significant predictive capabilities, right? And build dashboards for syndicate desk analytics, right? So let us move on to the next cell and refresh this. So in this case, similar to before, we have deal ID, investor ID, relationship score, request size, right? This is the number of shares are going to get allocated, yes or no, and then allocation size, right? So pretty straightforward. Hopefully that makes sense. Let's look at an example of a linear regression now. Now, if you look at my data science channel, I discuss this quite a bit. Any kind of classification problem is either binary, like we just saw, zeros and ones, true or false, yes or no, on or off, things like that. But you can also predict the labels, right? Like the size of a t-shirt. Is it small, medium, large, extra large, right? One of the criteria that definitely goes into making t-shirts is how much material is in the t-shirt, right? If you have more material, it's probably extra large. If you have less material, it's probably size small t-shirt, right? So that's a classification type of model. Regression models are quite a bit different. You're trying to predict some type of numeric outcome. So another example would be you can use regression or classification models to predict the weather. If you're using a classification model, it would be like, is it going to rain tomorrow? Yes or no? Is it going to be warm tomorrow? Yes or no? That would be a classifying type of model to predict the weather, right? If you want to predict the temperature for tomorrow, that's a regression model. So remember, regressions are numeric and classifiers are binary or labeled data. So in this case, We are using a linear regression model. There's a whole bunch out there. I discuss all kinds of linear, sorry, not linear regression models, but all kinds of models, including linear, but there's probably about 35, maybe a little bit more than 35. But I discuss that all on my channel on a bunch of different videos I put out. So check that out if you're interested. So again, we have the data. We are feeding everything into a data frame. And again, we're looking at our independent variables, right? So this is what we're trying to use to make this kind of prediction. Is an allocation, is a deal going to be allocated to a specific investor or a group of investors or whatever, or corporation, enterprise, bank, whoever's buying the stuff. And these are the independent variables, right, that we use for the dependent decision. So we go ahead, set up, run the regressor, and then create a plot. I'm looking at the R squared over here. So R squared, higher is better. You'd want to see like 0.97, 0.98, 0.99, and that shows you the goodness of fit. So this is actually a pretty decent model. It's doing a good job of predicting all these little data points over here and at which actual allocation and predicted allocation, like how closely are these to the regression line. So the diagonal regression line is the goodness of fit line. If all of these blue dots are pretty close to the line, the goodness of fit is going to be higher. You're going to have a higher R squared, right? And a lower RMSE. This is root mean square error. This is going to be lower and this is going to be higher. The model is performing better. If not, you would need to train the model on more data points. Remember, we're looking at only 4. That's not a whole lot for these types of models. We only have tier encoded, relationship, past, participation rate, and requested. If you had dozens of features over here, you could train the same model and get a much better R squared. We just don't have that data. I mean, I could create some more, but just trying to illustrate the point of this concept here. But again, like 0.93 is a pretty decent R squared, so the model is able to learn the data and make generalizations into the future about what's going to happen next. And probably a good next step would be to use the trained and tested model. The model's fit right here. It's making predictions right here, just like you saw at the classifier. So it's ready to go. You can put in any type of data you want. I didn't do that in this video. I do that a lot, but not every single time. But once you put in these 4 features and you run the model that has been trained and tested, it's going to spit out a 0 or 1 here, and this is numeric this time. Before it was labeled data or it was categorical data. You could call it either one. This is going to be numeric data, right? So the 0s and 1s look the same, but they're actually different data types. But you can determine based on these inputs over here what is going to be the output, and 93% of the time you are going to be correct. Okay, so hopefully that makes sense. I think it was an interesting analysis. What did we actually accomplish here? A couple different things. Simulated IPO deal allocation with investor tiers, relationship scores, past participation rates, and requested sizes of number of shares. That's how many number of shares you get. You delegate out or deal out, right? We built a classification model and regression model. The classifier was first, the regressor was the second one, right? And predicted allocated amount based on those features. And we visualized the actual versus predicted allocation using Plotly. This is the regression line that you see right here. So I am going to wrap it up here. I think that was good coverage. Oh, I don't need this though. I think that was good coverage. I learned quite a bit when I was doing the research for this. Hopefully that was enlightening and informative and somewhat educational to you guys too. I like to put these together for learning purposes. Okay, so I'm going to wrap it up right here, and I will see you guys in the next video. Goodbye.